Our talk is accelerated verification of parametric protocols with decision trees, and this work is cooperated with Typhon Cao, David M. Jensen, John Pang, Xiao Tao Wei. Our talk is composed of 4 parts. The first one is an introduction of parameterized verification of protocols, and its difficulty, and the limitation of the current research. The second introduces how to learn invariance with decision trees from a datasheet obtained from a reachable state set of a protocol instance. The third one is to apply this learning technique to parameterized verification. Fourth, we introduce our experiments. The last part is on discussions and future work. Parameterized systems exist in many practical areas. For instance, there are cache coherence protocols and distributed memory protocols in the 2 figures. The difficulty of parameterized verification requires that correctness of any protocol instance with arbitrary size should be checked. Theoretically, this problem is undecidable. Practically, we can't check all protocol instances. Even when the size of a protocol instance is large, model checking the instance can't be completed. Limitations of existing works lies in 2 parts. Firstly, auxiliary invariants are needed to be found by people. Much manual labor needs to be paid. Secondly, no solid proof is given. Thirdly, we need to understand auxiliary invariants better. In this work, we introduce a decision tree-based learning technique to sum up symbolic formulas to approximate the behaviors of a protocol instance from its reachable state set. We develop a learning paradigm and incorporate it into ParaVerifier framework, which is devoted into a parameterized proof. In the field of machine learning, a decision tree is used for classifying examples. It is a flow chart. Its an internal node is a test on an attribute. Each leaf node represents a class label for a target attribute. Usually we use the decision tree to predict the value of the target attribute basing on the other attributes. For instance, we obtain 11 states from the reachable state set of mutual exclusion protocol instance with size 2. Each state map a state variable like n1 and x to some value. By the classical decision tree algorithm IC3, we obtain a tree, which is shown in the figure. Notice that a leaf node is returned with a label which is the most common value of the target attribute in the examples. So the classification is based on the most frequent value of the target variable. It under-approximates the data. And predicting the most likely value is not suitable for our verification. We need to accurately predict all possible values of the target variable based on the other variables. So we label a leaf node with a disjunction of formulas which record all possible values for the target variable. This slide has shown how to apply it to partitioning state space. Notice that there are 6 paths in this tree, each of which represents a partition of the state space. This algorithm shows how to make an extended decision tree from a datasheet if target attributes and the other attributes are given. Line 2 deals with the case that decision on the value of target attribute can be made at once because all the samples agree the same value on it. Thus the leaf node is returned with a label target attribute value. Line 4 deals with the case no more attribute can be used to classify target attribute, thus a leaf node with all possible values. Here we need record all the possible values of target attributes instead of the most possible value of target attribute. This change has been made for the use to classify state space completely. Line 6 begin to make branches. Line 6 picks the best attribute to classify samples. In order to make the classification best, we need calculate the entropy of every attribute of the dataset. Then partition, split the set into subsets using the attribute for which the resulting entropy after splitting is minimized. Or, equivalently, information gain is maximum. In order to verify that formula in the form of negation f is an invariant of the protocol instance, we call algorithm 2, we construct a decision tree to decide it. We only select the subtable data 0 which contains just columns covering variables of f and use it to create the decision tree, see in line 3. For each path, we transform this path into a formula, and conjunct it with any symmetry form of f, if it is satisfied, then a counterexample is found. For examples, f1 is an invariant because x equals true and n1 equals c contradicts any path formula in figure 2. But f3 is not because n2 equals t and n1 equals c is contained in the path n2 equals t and x equals false and n1 equals c. We can adopt 2 optimal approaches to make the datasheet smaller, then learn invariants quickly. One is to take advantage of the symmetry of the reachable state set. Secondly, we can use don't care values to reduce the datasheet further. After adopting the symmetry reduction strategy, the state space reduces from 11 elements to 7 elements. But we need not only check a concrete form, but also its symmetric form. For the Flash protocol in our experiments, the number of reachable states is 107,866,864, while with symmetry reduction and don't care values it is only 857,453. The latter is about 0.8% of the former. So the more complex the protocol is, the more benefit the symmetry reduction gets. How to use the DT deciding procedure? We extend the Paré verifier framework with this new invariant learning approach based on decision trees, see figure 4. Essentially, we use MRFI to get the reachable state set of a protocol instance, and transform the state set into a datasheet. With the algorithm DT decide, we explore the datasheet and construct decision trees as necessary. The trees act as an oracle to check invariant candidates received from InFinder. We have applied our new framework, figure 4, to 6 benchmarks. This table gives a comparison of verification time and memory consumption for the benchmarks between the based oracle and the decision tree based. At first sight, for small protocols, mutual exclusion, messy, the decision tree based oracle is slightly slower than the BDD based oracle, but requires less memory. However, for large examples the decision tree based oracle performs much better. The last slide is our conclusion. We use decision trees to learn invariants from a datasheet describing the reachable states of a protocol. We apply the learned invariants to accelerate parameterized verification. We integrate the decision tree-based learning technique into Paré verifier and use it as an oracle to learn invariants for parameterized verification. The experiments show that our decision tree-based invariant learning framework can save memory and speed up parameterized verification for large protocols. Thank you for your attention.